This is a solution for question 4.6 in the FEEG1003 Thermal Fluids workbook. This is relevant to the version in 2016-17. Okay, we've got a problem and we're going to use Buckingham Pi way of analysing and doing dimension analysis. There are other ways to do it. The Buckingham Pi is pretty robust. There is the Rally method, which is slightly simpler and quicker. But the Buckingham Pi one is the one we teach you and the one we'd expect you to use. So we've got a problem and we've got 7 parameters that are given to us. So we've got the force, which we'll denote as Ft. Okay, and it's good when we get these parameters first out to actually write out the fundamental dimensions of each one. So being force, it is mass length times the -2. We have velocity V0. That's the diameter. Got dynamic viscosity, angular velocity, density, and C, which is speed of sound, I believe. Now, Buckingham Pi states that we have n number of parameters composed of m number of dimensions. We can form n minus m dimensionless groups. So we've got 7 parameters here, and you can see just from the first one, force, that we've got mass, length, and time. This are 3 fundamental dimensions. So we can arrange these into 3-dimensionless, 7 minus 3 into 4-dimensionless groups. Now what we're going to do first off, so we figured that out. We need to choose some repeating variables and some fixed variables. And the way that Buckingham Pi works is that for our 4 groups, we can have one of these parameters will only appear in one group only. So we need to choose 4 to be fixed, and they will appear once in each group. And then the remainder, the other 3, are going to be what we call repeating variables. So they're going to appear in every dimensionless group. Now, some of the repeating variables might disappear as part of the process, but that's the way we're going to set it up. So we're going to choose 3 to repeat. So I'm going to choose density. Okay, so what we do is when we choose repeating variables, they should be, first rule of repeating variable club is they cannot form a dimensionless group by themselves. And looking at that, it's impossible to. So we've got a length times the -1, and density is mass per length cubed. Okay, so they can't form a dimensionless group. They should also be easy to measure, and for that you really need to use your engineering judgment. But we'll choose those because it gives the one of the dimensionless groups comes straight out in the answer, which is the one we need to use for the second part of the question. Okay, so what we do now then, so these 3 are going to appear in every one, and then group 1 will have Ft in it, group 2 velocity, group 3 viscosity, and group 4 the speed of sound, the velocity. Okay, so we write them out as what we call pi groups. It's best not to ask why, but just to accept that that's the way we're going to do it. So we write for our first dimensionless group, we'll call that pi 1. So we're going to have rho, T. Okay, this is our first group. What we do is we raise each of the repeating variables to a power. can call them whatever you like. So I'll call this A1, B1, C1. Okay, and we leave the fixed variable alone, and we don't raise that to a power. This is just the way we do it. Okay, now we're going to write out the fundamental dimensions of each of these. Okay, so expanding it out, we have mass, length to minus 3. Okay, and then that's raised to the power of A1. Omega is times the minus 1, raise up to B2, B1. And then D is length, so that's length of C1. And then finally the dimensions for this, the force, so mass, length, times the minus 2. Okay, take care with that and take care with the next step. What we're now going to do is equate each dimension in turn so that it's raised to the power of 0, so it's dimensionless effectively. Okay, I'll start with length. So basically if equal to 0, so we've got length here, so minus 3a1, so 0 equals minus 3a1. Go along, there's another one, plus c1, and then plus another 1, plus 1. Okay, just take your time with this step, because sometimes it's easy to miss them or write them down incorrectly. Next one is time. So again, 0 equals, and we look along here for all of the time terms. So time to the minus 1, so 0 equals minus b1, and then we've got a minus power minus 2, so minus b1 minus 2. And then finally, mass. Okay, so the mass term straight away, so equals to A1, moving along, plus 1. Okay, and then we can work out the values of A1, B1 and C1, okay, and then put them back into this formula. Okay, so it's pretty easy to work out, so A1 is minus 1, B1 equals minus 2, and C equal to minus 4. Okay, so we can put them back in here now. And then we can write this out in a standard form. So our first pi group, our first dimensionless group, I'll do it up here because I'm running out of space, is equal to ft over rho omega squared into 4. Okay, that group is dimensionless. Okay, in terms of answering the second part of the question, that first pi group that I've generated is what you need. Okay, so the whole idea of a dimensionless group is it can be used for scaling. So, for example, if you have a wind turbine, the Reynolds number across the blade tip might be 1 times 10 to the 6, a million. If we want to do some experimental testing of a turbine, we wouldn't build a full scale model. So what we would do, sorry, computer's hibernating. So what we do, we build a scale model and put it in a wind tunnel. We try and keep the same Reynolds number if possible. It's not always the case to be able to do that, but that's what we try and do. And then we know that the flow regime over the tips of the blades is the same. So what we can do, we can write out this equation twice. So once for our model scale, which we'll call M. So and then assuming that we're scaling correctly, we have the same equation, but for the full-scale prototype, which we denote with the denominator, sorry, the subscript P. So exactly the same. But this time all the values for the prototype. Okay, I can't remember the question off the top of my head, but you're asked to find one of these forces. I can't remember which one, if it's a model or the prototype, but if you look at the question, you're given every other variable apart from one of these two, which is your unknown. So you can basically just rearrange. Okay? Right, I'm not going to go through the whole rest of the question in detail like that, so remember that methodology. But I will give you the dimensionless groups and a bit about what we can do with them to rearrange them at the end. But remember, we've got 7 properties, 3 fundamental dimensions appearing at least once. So we've got 7 minus 3 is 4 groups. We choose 4 parameters that are going to appear once only in a group, and then 3 of them repeating, so they appear in all. Okay? Raise them all to these sort of imaginary powers. So we raise the repeating variables to these powers, and then tag on the fixed variable, put in the units, and then write these expressions where the overall sort of exponent is equal to 0. So 0 equals, and then go along and just equate all of these powers to raise the dimensions to, and then solve for A, B, and C in this case, and then we can write it back in and form a dimensionless group. It's always useful if you really want to check you've done it right, is to put the dimensions in here as well, and just check that they all cancel out. Okay, so now I'll just go through the answers to the other pi groups. Okay, the next pi group, so for pi 2, we're going to use B0 as our fixed variable. So we do the Buckingham Pi analysis. We get V0 over omega d. And you can see here that when it came to density, that one actually disappeared out of this dimensionless group. Okay, so that's how Buckingham Pi can work. So in order to force a dimensionless group, the density's gone. So there's no mass term in here. Okay, got length times the minus 1, and then length times the minus 1 there. So this cancels and becomes dimensionless. The third pi group is the dynamic viscosity over density, angular velocity, and square of the diameter. And the final one equals C. And what we can do with dimensionless groups, because they're dimensionless, we can do various algebraic manipulations to get them, to force them into a form that we're probably more familiar with. So I can already see this one here has the potential to be Reynolds number. We've got a length term, we've got a density, and we've got the viscosity. So what we can do is we can invert groups, because the dimensions of the numerator and the denominator are the same. So we can invert them. We can also multiply or divide groups with other dimensionless groups. Okay. So what we can do here is if we invert pi2, omega d v, omega d and v naught, then multiply it by this one. You'll end up with Reynolds number. Oh. Sorry. Rho. Okay, so the ratio of kinematic to dynamic, and then finally, because this is the speed of sound, we can manipulate group, the fourth pi group and the first pi group to basically cancel out the omega d, and you'll end up with v naught over c, so the velocity divided by the speed of sound, which you might know as the Mach number. Okay, so we can do that with dimensionless groups. If you do this a slightly different way and choose different repeating variables, then what you sometimes do is you end up with these straight away. So there's different routes through. There's no real incorrect way of choosing which variables to fix and which to repeat, but what you will do is get different groups out, different dimensionless groups if you do it a different way. Okay, but you can still combine the groups, so divide one by the other, multiply, invert them, to ultimately get to the same answer as had you gone another route. Okay, so these are the other three groups, but it's that first pi group involving the force and that equation that I showed before that you can do, and you can plug in the numbers, one set of numbers for the model, one for the prototype, just one unknown, and then you get the answer to question 4.6.